Okay, sir. Stream has started.
Started, huh? Okay.
Yes, sir. Sir, I think we can.
Shall we start? Start, right? Okay.
Yes.
So good morning to all of you. It takes great pleasure in welcoming you to all to this web talk, popularly called webinar. Maybe thanks to the lockdowns, this term is very famous now. So I feel privileged to introduce Professor D. Eswar Reddy to this diverse audience. He is currently professor at Indian Institute of Astrophysics, Bangalore, a world-renowned institution in the field of astronomy research. He is also program director for 30-meter telescope, Indian Coordination Center, called TMT India, and member of the governing body of TMT. TMT is a joint international project between 5 major countries. So India contributes significantly to this prestigious project, which is costing around like just now Sir spoke, it is around like 20,000 crore, a 3 billion project. So this is a major scientific project involving many scientists and engineers. So I think I see many engineers here. So that's why I'm mentioning here. So in the second half of this webinar, he will talk more about this project, definitely. So incidentally, Professor Eswar Reddy is native of Kurnool district in Andhra Pradesh, where DIIM Kurnool is also situated. His scientific journey, starting from his childhood, is truly inspiring story, which will require separate session. Definitely, later we will have a session with him related to that one. It's really an inspiring story. So briefly, he did his PhD from Indian Institute of Astrophysics, later to join back as professor in the same place in IIA. Meantime, he worked as a research fellow in USA for a few years. His research work is in the field of stellar spectroscopy. So in his research group, data is collected and analyzed from tens of thousands of stars from world's most powerful telescopes. And today, in the first half of his in this webinar, he will talk about his recent breakthrough work published in Nature Astronomy. This is really truly a proud moment for Indian astronomy, I would say. We all know that lithium is lightest element in the periodic table. The unknown story is that it is one of the 3 elements produced during the Big Bang, the other 2 being hydrogen and helium. So his work throws light on the evolution of lithium since its creation from the Big Bang. Also in the second half, so this is the first half of his webinar. In the second half, he will talk about the current astronomy facilities in India and future upcoming facilities. Definitely TMT is one of them. So this is about him and then about the talk. So now I would like to invite our Honorable Director, Professor DVNL Somayajulu, to give you a brief inaugural speech to kickstart this season's Astro Club activities. I have to mention here that Astro Club was started last year in DIIM Kurnool. So inaugural speech was given by Professor SVM Satyanarayana from Pondicherry University last year. He is also our BOS member, Department of Science. So today's session, after director's speech, will be moderated by Sirish, one of the club coordinator. Now over to Professor DVLN Somayajulu, sir, for his inaugural speech.
Okay. Thank you, Dr. Murali. First of all, I welcome the great personality, Professor Eswar Reddy, to this webinar. Thank you, sir, for showing keen interest in supporting the talks for the benefit of our students and other community. I think I came to know that many people, even outside DIIM Kurnool, also joined this webinar. And also I came to know that this talk is also telecasted through YouTube channel. So again, I thank Dr. Murali, head of the Department of Sciences, for showing keen interest in arranging webinars. In fact, every year we invite eminent people from different parts of country to deliver talks for the benefit of our students and also for our outside students' benefit. And today, in fact, this is the second webinar they planned as part of this club. Our students are very active, but due to lockdown, these webinars are started a little bit delay, but by this time every year normally a lot of activities are happened even in the last year. But today in this year the activities started with online platform. So first of all, I welcome, and again I thank Eswar Reddy for showing interest to deliver a talk for benefit of all of us. Good morning to one and all. Today I'll briefly touch upon Indian astronomy and the importance of data science in astronomy, because India has rich traditions in astronomy. In the beginning, astronomy is basically observational science. A lot of astronomical observations were made at first to get more accurate calendars, which was crucial for rain prediction and agriculture. In the later periods, Indian astronomers made many valuable contributions to world astronomy by combining their analytical skills with observational data. So, in fact, in data science, observational data is very large input taken into consideration to develop suitable prediction models by widely using popular machine learning models. So, in fact, astronomy is one kind of application domain as far as data science is concerned. And Aryabhatta gave a geocentric model of the solar system, which made surprisingly accurate predictions even in the 19th century. Neelakanta's model of the solar system, the most accurate in the world until John Kepler's model in the 17th century. Astronomy has always been a field that required extensive observations. Tycho Brahe's incredibly accurate observations spanning decades were instrumental in allowing Johannes Kepler to come up with the elliptical orbit model. Recently, the first photo of a black hole was published. Normally, such a photo would have required a telescope much larger than what is available right now. But thanks to the work of Dr. Catherine Bowman, it was possible to image the black hole with only a few smaller telescopes. Astronomy is different from regular Earth level physics or chemistry in that the data collection is often over much longer timescales. The sheer vastness of space means that even amateur astronomers have a good chance of spotting important objects or events that scientists may miss. Amateur astronomers often contribute valuable data in the changing brightness of stars and supernovae. Having good data science tools and fundamentals that are available today allows astronomers to better process all the data. It is now possible to derive far more data from the same sensors thanks to much better data processing algorithms. Data science is crucial for the future of science, as data sciences and as data science enable us to properly understand and utilize observation data. I'm sure the participants will get a great, immense benefit from this webinar. In fact, I am also expert in the field of data science. Since the today's speaker is from Kurnool, I'll be happy if he visit Kurnool once and then share some of his experiences physically with our students also and faculty. And our Department of Sciences is very keen in taking up projects on the astronomy, application of data science in astronomy. In a way, it is known as astromoanalytics, right? Every analytics is associated with some data, but this astronomical data is very, very large in size, I know. So our Department of Computer Science and Engineering and is having expertise in this field of data science. So definitely we will take up some projects if the opportunity is given to our students. So I would like to leave you with an interesting quote related to astronomy by Lawrence Krauss. Every atom in your body came from a star that exploded, and the atoms in your left hand probably came from a different star than your right hand. Astronomy is an intriguing field. I hope you all learn interesting concepts today from this webinar. And in fact, 8 years back, one of my undergraduate student who passed out from NIT Warangal, he approached me to do PhD in the area of astronomy. with analytics, data analytics, 8 years back, right? Who is a government employee today at government of Telangana, right? So, but those days we are also new with understanding of data science. But now today at Kurnool we have good expertise in the area of data science. Definitely we can take up some good projects by integrating the expertise from the astronomical domain with the data science domain, so that some fruitful results can be obtained from this process. So with these opening remarks, once again I welcome Professor Eswar Reddy, Program Director from Bangalore, to deliver his webinar. Thank you, sir. Thank you.
Thank you very much for your kind words, and also the links you made from data science to the astronomy. Yeah, that's one of the big field. And let me also express my thanks to Dr. Murali Devaraj, and first contacting me and then providing this opportunity. Of course, you as the IIIT, the Kurnool. So I didn't know this until I came into contact with Dr. Murali, that we have this IIIT in Kurnool. But then I'm very happy now to give a seminar to the one which is in my native district. So thank you very much. And should I go ahead, start sharing my screen now?
Yeah, please, sir.
Yeah, I'll just do that.
Murali, before starting his lecture, do you want to say anything?
Are there anything which I need to know?
No, sir, you can start your speech.
Okay.
Okay, sir. Thank you, sir. Start, sir. Right.
So you are able to see my screen full thing?
Yes, 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 yes.
Okay. So I will, it's very difficult now because let me see, I will go through slowly, but then I'm not going to go any details, and then give you some flavor so that you can appreciate the results which I'm going to show. So as you all know that the lithium is the third element in the periodic table, which is very light, lightest among all the solids in the periodic table. And then you also know that it has 3 electrons, 3 protons, but then 4 neutrons. So that's why its atomic mass is 7. So, and you can see on the right side upper corner, which floats in the water, it is in silver in color. Okay, now I'm going to talk about lithium, how it evolved in the stars. Okay, you can see the background stars and then lithium. So about lithium trivia, which we all know how useful lithium is in day-to-day life as well. Hello. Day-to-day life. And then it is used in even the medical sense, you know. People who have a depression, people take lithium carbonate in small doses. It seems this is known for quite a long time. It's used in the medical sciences, even during the Roman era. And then the people who had, you know, depressions or, you know, maniac attitudes used to bathe in, you know, some of the alkaline places where you see these geysers, you know, hot springs, things like that. And then those people used to get better off. So, but then lately people came to know that those contains a lot of lithium in that those geysers. I think that we do have in some of them in Himalayas as well. and people go and take baths and then drink those waters, and then people feel happier. So lithium content, even in our own body, used to give certain benefits, particularly about well-being of your neurological senses. So that's one medical aspects of it. And there is a lot of lithium on Earth, particularly in seawater and salt lakes, dry salt lakes. And then a lot of lithium is available in different forms. And now much of the lithium people know lithium batteries, which uses our phones and things like that, few milligrams. And then currently now the cars, which is quite important. So the lot of lithium is now, people are looking for mining these things. So much of the lithium now is available in Southern America, South American countries. 50% of them, it comes from those countries, the mining. But there is enough lithium for billions of cars to make. It's nothing too much worry, but of course, one has to find the commercial way of digging these mining. So the cost is coming down. So that's simple about lithium. Now you wonder where this lithium is connected to the stars. I will just take you some of those issues. So let us now talk about quickly about evolution of stars. So as you know, all the stars form from the dust, interstellar medium and gas. And then look at these, the leftmost corner where you see the lot of dust, the small stars forming. So there are two streams of evolving of those stars. One is they go the upper channel. If stars are less massive, say sun-like stars, our own sun, or slightly more massive than the sun, those are called small stars, say. They become red giants. They become bigger and cooler, can I say. And then later on, they evolve, losing that mass. And then that mass you can see outside the center, like a planetary nebulae. And then they become a white dwarf. Basically, those are dead stars. And these are the degenerate material. They contain mostly electrons, electron degenerate dwarfs, hydrogen ions and electrons. The another stream is if the star is quite larger, and then they evolve much faster. That is bottom channel. They become much bigger red giants. Then they have huge mass, and then they blow up as a supernovae. The violent explosions. They can become some neutron stars and black holes. So there are many of those things. So this is the two channels which you go through. So today we are mostly concerned about the stars which go the upper channel, that is small stars evolving to red giant and then planetary nebulae. So where the lithium comes from in that channel. So the entire stellar life, stellar evolution, that star's life is coded in a diagram so that it makes easier for people to understand star's life, So one side, you can see the y-axis, that's the luminosity, is basically brightness of the star. And then x-axis is basically the temperature of the star, okay? Surface temperature, not the internal temperature. Internal temperature is different, which is a core temperature, which has millions of degrees. When you plot these in these diagrams, the stars of various types, you can see they follow certain patterns within the HR diagram. This pattern is used to understand the star's life, where it is, if it is a massive star, how long it takes for it to become white dwarf or neutron stars, things like that. For example, when you see m is equal to 1, that is the solar mass. That's the sun mass. So sun mass is normalized, everything is normalized to the sun mass. It is difficult to say in kgs, because these are huge. For example, if you want to the sun's mass, it's maybe the 10 power 26 kgs. It's a huge, people, it's very difficult to remember as well. So everything is normalized to the sun. If I say 2 solar mass, that means 2 times of the sun, something like that. If you look at solar mass, m is equal to 1, the way it evolves, this yellow line is actually the main sequence stars. That means all the stars have a like a solar life. Currently our sun is on the main sequence, So when it loses the central hydrogen, so the stars move up this white thing, m is equal to 1, and then they become slightly bigger, and then they follow this green, which is called red giant branch stars, and then they move on. So there is a tip, it's called red giant branch tip, and then for some reasons it will come down in the HR diagram, and then again they go up, they evolve, and then become white dwarfs. This is a basic stellar evolution. You can see when the stars are in the main sequence, the core is actually hydrogen burning. The stars are burning hydrogen at the center, okay? But then when the star starts deplete that central hydrogen in the core, and then start moving towards red giant branch. Now helium is the core now, okay? But then that helium doesn't burn. It is a inert, okay? Because just is an ash from the nuclear reactions from the hydrogen. So the ash is now at the center. And then now you have a hydrogen burning in a shell, and then which gives most of the luminosity or brightness, okay? So then once the temperature at the core reaches a level where the helium also starts burning, and then stars go to different phase, which is called the red giant branch, which is this the color here, magenta color, that the helium burning phase it gets into. Okay, that's called the red clump stars. Okay, that's we just stop there because I don't know how much you all appreciate this entire because many of them are, I don't know, the BSc and MSc and then engineerings. Some of them probably maybe be having during intermediate about basic stellar evolution, but that's what it is happening there. Okay, there is a core hydrogen. Once the hydrogen gets depleted at the center, and then the stars moves the red giant branch, and then once helium also starts at the core, and then the stars become red clump stars. Okay, how do we know all of these things? How do we know even the temperature? How do we know the brightness? How do we know, what is there in the star? How much carbon is there? How much nitrogen is there? How much lithium is there? So this all is basically spectroscopy. You all know the spectrographs, and then which has gratings and things like that. And then light passes through those gratings, and then these gratings, depending on the number of lines in the gratings, it splits into number of wavelengths. For example, if you pass white light into the prism, you see, the 7 or 8, yes, 7 colors. Each color is a one line, red, blue, green, things like that. But then what happens if that prism can split into so many colors? That's called the spectrograph or grating. So depending on the number of grooves, the grating, you can split the lines, into 1,000, 10,000, 1,000,000. So then you can see very fine structure of the star. So what I kept it here is, estimating of the temperature and metallurgy. You can see the top top spectra, which is resolution is 3500. Resolution means delta lambda by lambda. Okay, so delta lambda is the wavelength separation between the two lines. Say, even the single line, what is the width of the line? Okay, and then the lambda is at a given wavelength. What is the resolution? That's what we look at it. So higher the number means, the better the resolution. Better the resolution means you can see more fine structure, more number of lines. See, for example, if you can look at it, the same line here, R is equal to 3500. You don't see on the top, but when you come to down next one with the 10,000 resolution, you can see few more lines. But when you come to 60,000, the same lines are split into many different lines. Now you are becoming much more better in seeing them. It's like a visibility, So when you see far away thing, you can see the mountain, but when you come to the closer and the mountain, you can see a tree and then many number of trees and then small trees, and of course berries on it. That's what it is. So it's as if something like since we can't go to the stars, and then we have to use better and better, lenses to see the star very close by. That's what we are doing it. The more number of lines means we are reaching very close to the star. That's what we are doing it. And these lines contain, each line is a different wavelength and which corresponds to different elements. For example, the one which is in the center is a lithium line. It's a very strong lithium line. And then the other lines correspond to many different, iron, silicon, magnesium, and things like that. And then, of course, now, how to get these things? And then we had to, of course, one is the lab, you use it, to pass through these various material which we know on Earth, and then get a lab spectrum, and then you identify these lines. And then you can look at these line strengths, and then, of course, you create a model existing the physics, radiative transfers, if you pass through various gases, how these lines are seen, and then how to quantify those amounts. That's what there is the sophisticated models people make it, and then understand the chemical composition of the stars. That's what is the abundances. Abundance means the quantity of particular element in the star. And these quantities differ from star to star depending on when they're born, where they are born, and what are their environments like, That's what we do, basically. Using these things, we estimate these abundances and then find out the star's ages and then evolution and things like that. So now, coming back to the lithium, that's our main focus in this thing. And as Devaraj Murali pointed out in the beginning, and then most of the lithium comes from the Big Bang. Big Bang means, the universe had a beginning, okay? The universe had a beginning, and the beginning was approximately 13.45 billion years ago, okay? That's very, very long ago. The universe took a seed there, and then within those few minutes, the many elements formed. Some of the elements formed. Those are hydrogen and helium, along with the lithium also formed in the Big Bang. In the Big Bang nucleosynthesis, that time there were no other elements were there. There were only baryons, like protons, neutrons, electrons, and things like that. That was matter just came into that. As soon as those electrons, neutrons formed from further fundamental particles like bosons and things like that, and then elements start synthesizing themselves. That's where the lithium comes from. The current state of the models, nucleosynthesis, that's called Big Bang nucleosynthesis, estimates lithium some amount. I don't know how much you appreciate this. I don't want to go into big numbers. So that's why the astronomy got simplified by using certain standards and then normalizing these bigger numbers into manageable numbers, which we can remember and then correlate easily. So the way the lithium is in any star, okay, is represented by something like log A lithium, the logarithmic scale, which is basically a number density of lithium atoms in the logarithmic scale divided by number density of hydrogens plus 12, which is a normalizing factor. So this hydrogen is assumed as number 12 also. So if we take that into as a definition, and then the Big Bang nucleosynthesis, which is the state-of-the-art models, which is all the current physics and experimental data putting together, all the laboratory work of nuclear reactions, they come up with the best number, which is 2.7. That is a primordial value. You can think of it. Now, if you see, but then Earth has 3.2, and the current value in the interstellar medium is around 3.3. So the current interstellar medium is basically 4 or 5 times more than the Big Bang nucleosynthesis. That is from, so over this evolution of the universe from Big Bang to now, about 13 billion years passed by. And during this time, the lithium got enriched in the universe by a factor of 4. So that then it reached to the current value, which is around 3.3. So the age of the Earth is around 4.5 billion years. So you can see the 3.2. So it's not too much. But on the other hand, other elements grew, for example, iron, more than 1 million times over the evolution of the universe, like a magnesium. These are all more than 1 million times they grew. But the lithium grew very slowly. That is mostly because stars are destroyers of lithium. That's all we know. So that's where the lithium comes from, most of the lithium Big Bang. And there is an issue now where even a factor of 4 came into existence. So now what are the sources for lithium? Because people know that stars don't produce lithium. They only destroy the lithium. But then what else can produce this lithium in the universe? So there are 2 channels for lithium productions. One is galactic cosmic rays people talk about, because there are very high energy particles within the universe, which can smash like a larger atoms like oxygen and carbon, and then they produce the smaller atoms from carbon and oxygen. So they produce helium and lithium. That's one aspect of it. But still, we don't know how much really that can produce. It is not accounted for the entire 4 times. Stars also produce lithium by fusing this 3He and 4He. There's a helium, helium in the stars. They produce beryllium first, and then beryllium can decay into a lithium. This is one of the issues they can produce in the stars. But what is not known about the stars is you can produce in the stars, but then you never bring it up to the surface because lithium gets destroyed at few times a million degrees. But few times a million degrees is very easy to attain in the stellar interiors, in the stars' interiors. The central stars have a very high temperature, much more than these few million degrees. For example, you can look at this production mechanism, this side, the left side of my slide. This particular reaction, which produces the beryllium channel, which occurs around 20 million K, 10 power of 7 K, the 20 million degrees K. It's a Kelvin degrees, okay? But then you can see the lithium gets produced there quickly. Then the problem is if you don't bring that lithium into cooler places, that get destroyed easily. very easily. So there should be some mechanism as soon as lithium gets produced in the hydrogen burning cell by fusing this 3He plus 4He, then you don't see lithium on the surface because it gets in between from the center to photosphere. There's a huge temperature gradient, which is many places exceeds these this million degree scale. So they easily gets destroyed. The best current stellar models, nucleosynthesis models, they don't expect any lithium from the stars. They don't expect. The models don't predict any lithium enhancement in stars. They only destroy lithium. That's true. Most of the observations do show that lithium gets destroyed in stars. For example, the standard models, which we looked at it, this is in the diagram, you can see lithium gets destroyed in all the stars. By the time they reach evolve to red giant branch. Okay, red giant branch means, which I talked about, evolved off the main sequence. Once stars move away from the main sequence to red giant, what happens during the red giant means there is a lot of convection is there. Convection means the mixing happens from photosphere to the hydrogen burning cell. Okay, there is a convection channel. Okay, so what happens in the convection is whatever the material you make during the hydrogen burning cell, that will be transported to the photosphere, and then whatever the material, cooler material in the photosphere, which goes down. So now in this process, what happens is the earlier, which was lithium, which was there on the photosphere, which has much more, then goes down to the center. It gets destroyed, lithium there. Somehow also gets produced, but then it mostly get destroyed. So now the material which is less lithium, which is depleted, again brings back. So in this convection process, what happens is photospheric lithium gets depleted slowly as the star ages because of this convection process. That is clearly seen in many stars. For example, our own sun, though it is not even evolved, there is very less lithium in the sun, even compared to our own Earth. See, when during the formation of our own solar system, okay, lithium escaped the destruction, which is there on Earth, because Earth doesn't have that very high temperatures to burn this lithium. On the other hand, the sun has much higher temperatures, so that it can destroy. So there is a very less lithium. It's almost like a factor of 100 less lithium in the sun compared to Earth. So basically, the lithium gets destroyed in stars. Okay, that's what general theory, and then most of the observations. I can see these observations here. You can see that I showed you some diagram, temperature versus the luminosity. These are actual observations. These are the measured the brightness and then temperature in terms of a color. You can see this actually the right side of the diagram, which is the panel, which you see this. It is in a cluster, large cluster. The stars have different colors, and then the color is actually correlated with the temperature. You can see in the beginning, that's called the main sequence, where our sun-like stars reside. When the stars move up, so this becomes a red giant branch, and then at the end, at the topmost, is called the RGB tip, and then basically stars come down here and then go up. That's why it happens. Now, for the same stars, we looked at the lithium abundances here, okay, on the left side of the panel. You can see how the lithium gets destroyed. So x-axis is the lithium on the left side panel, and then it comes down from the main sequence quite a lot, okay, and then it almost becomes no lithium in the stars. That's what we all know. So the model predicts no lithium. Most of the observations do predict, show no lithium in stars. So this is all understood. So that's why it is a known. So cellular theories is validated by these observations. Of course, now you need to always look at outliers. Whenever you are looking into a problem, either engineers or scientists, what we have to look at is outlier fellow. Why that fellow is outlier? Why is so different? If there are 1,000 people, why only one fellow is a different, say, color or and looks abnormal? What is the problem there? There must be some real big clue there. That's what people look at it. There is an outliers always. The outliers provide a lot of insights into your problems. I think you always should remember these anomalies, that's outlier. So is a key to understand things better. So don't go with the mainstream. Sometimes it doesn't work. So what happened was some 40 years ago, when people were looking, this was a big accident in one of those stars, which turned out to be a red giant. Suddenly they discovered a line, it's a huge lithium line. You can see the spectra from the bottom of the panel on the right side. That's a huge line, And then normally all the lithium, all the normal stars, you don't see any lithium. That is a top spectra. That was a huge thing. That was by accident they discovered. And then since then, people discovered here and there, few of them, but then it was not a mainstream at all where this lithium is coming from. And then in over 10, 15 years, people came up with various theories for this lithium abnormality. Another thing which came very recently is the discovery of planets around other stars in the galaxy. That's a new one, just 25 years ago, 1995. So that was a huge thing. And then people thought maybe because Earth has more lithium, so maybe too many Earths can plunge into the star when star becomes a red giant. They can create more lithium. That's one of the theory. Okay. And then another theory is maybe this lithium was not mixed well in the stars. So mixing was less efficient. And this is mostly because this is mostly the part of the interstellar medium from which the stars form. So this preservation due to suppressed mixing was taken out, because in some of these stars, we have seen even 10 times or even 100 times more lithium than interstellar medium. It cannot be more than the interstellar medium. So then there must be something extra lithium is produced in these stars. This is the issue. So now the competition is between about planet plunging versus stars themselves produce, and somehow lithium is transported to the higher lithium is transported to the surface. These are the two major issues which came up. This actually, I started this when I was in University of Texas, Austin, and then that's also for me an accident, because I was interested in much more evolved stars before the stars are dying. So then I came in my own data, there was one star which has a much larger lithium line. So that's what one we published in 2002. So that caught my attention about the lithium problem seriously. So apart from lithium, then we also said these stars have large amount of infrared excess around these stars. That means they have a dust cell around the stars. That's what we said those days. So having the dust cell, some of the theoretical problems came into, oh, okay, that's great. So Earth has more lithium. If you pump some, if these stars have more number of planets around them, and these when the stars they grow, and then the orbits can be perturbed, and many of these lithium-rich planets get into the stars. And also, according to the models, they also produce infrared excess because of plunging into the star. So that fits into nice theory. But then that was not convincing for us. Then when I came back to India, then we started, of course, the students are assays. When we had, I had two students working for me. And then one of the students, Kumar, and we devised a method using large amount of data, systematic studies. Let us understand this lithium. When we did this large amount of data using our own telescopes in India, so again, using the HR diagram, that is luminosity versus temperature, what we discovered was, it was a bit surprising for us, all the stars which are the lithium are in a very narrow range of brightness, very narrow range of brightness, very small narrow range. You can see in the right side diagram, again, the lithium versus the luminosity. Suddenly, at a certain brightness, the amount of lithium goes up quite high than the normal. The normal is somewhere here down. You can see around 1.5 or something. So that gave you a clue that it's not because of planet plunging, because if it is because of the planets, that can happen anywhere in the star's lifetime during the red giant branch, not necessarily during a certain brightness of the star. So then we took it out, that theory out. But still we didn't know exactly at what evolution it comes from. Though brightness is known, what happens is now, one is stars are going up on the red giant branch, and then they're also coming down during a helium burning stage. So these are overlapped. This overlap is extremely difficult to disentangle because there's no way we can measure temperatures accurately better than 25 degrees still to separate these. Either these stars are burning helium at the core, or whether they have just inert helium core at the center. So we don't know. So this is the way we started to understand whether these stars are really reticulum stars. That is, you can see this is a cluster, globular cluster. Globular cluster means these are very old, large number of stars. And then the same stars, if I put in the temperature versus the brightness, you can see that their evolution of the stars. You can see these RGB. See, most of the stars we are seeing here, but by using field stars, there is no way I can tell whether these stars are near this RGB bump or the horizontal branch. Horizontal branch means the stars which are burning helium at the center, or the stars which are just hydrogen burning in the cell. So we don't know. And you can ask, so what is the problem of observing these stars? But then there's no technology, there's no telescopes to get spectra for these very, very faint stars. These are very faint and these are very far away. I can get only, the brightness magnitude. To get a spectra, you need to have a lot of light, because you need to disperse the light into many number of lines. That means you need to have a large amount of light. So that is a difficulty process. So one way is I'm not going to go into these things. So one way is use large number of data sets, thousands and thousands of, and then whether I can see stars at, horizontal branch and then the bump. If I plot these are all the field stars. These are not clusters or anything. I can see there is a one large cluster here on the top, which are probably mostly or helium core burning. Okay. And then there is another one less denser, which are mostly the stars which are still ascending the RGB. That means they are still, the hydrogen is burning in the shell and the helium is at the core, no burning. So this is the way we got an idea that we did in 2019 with one of my students. This is a very key paper, but still we didn't know and the mechanism by which these are happening. Okay, again we use the same data. And then what our discovery was later on, I'm not going because just I want to conclude this part quickly. So what our discovery is basically, you can see this model. Model is the dashed line, the model, theoretical model. This is the state-of-the-art stars nucleosynthesis model as stars evolve. What you see is basically lithium gets depleted. And then that also you can see the stars also the following the same in general. But what you see this magenta red color, those are the lithium rich stars. What we discovered was all of these stars are having at the center helium burning. Okay, this is a different phase of the star than most of these stars. That is called red clump stars. So what we also found is, this is called RGB tip. This is the RGB tip where the center is a degenerate core, and then that explodes as a helium flash because the helium is at the center, and then start burning helium quiescently. As soon as that happens, stars come down to the red clump phase. You can see here all of these stars are red clump phase, the red stars which has a large amount of lithium. Okay, so in that case now what we said is lithium is not rare in these stars. Lithium is common among all these stars. Any stars which go through helium flash at the tip of the red giant branch, they produce lithium. That's a main takeaway. Okay. Now, of course, now we need to look at whether this production of lithium in these stars is sufficient to account the difference between the Big Bang lithium to the interstellar lithium. Okay, that is the new work is going to concentrate on that. That's about my discovery. This Nature paper is about that, and which has far implications about validity of Big Bang nucleosynthesis, and of course stellar models, things like that. So the greater useful thing is that. So quickly now I just go through astronomy facilities in the country. I am sure that many of you come from various institutes and colleges, and then I'm sure many of you know, and some of you may not be knowing, and I'm just go through very quickly the areas where, the places where we have this astronomy. See, these are the places where we have astronomy, and we can see the red is solar observations, people do, sun. And then there is optical and infrared observations. You can see those blue, and which is mostly from Indian Institute of Astrophysics controls. And you can see one on the top, Hanle in Western Himalayas, and then in Uttarakhand, Devasthal, and another one is in Tamil Nadu, and which is it's Kavalur, which is around 40 or 160 kilometers from Institute of Astrophysics. And there are, of course, world famous radio facilities in the country. One of them is in Pune. And there are many institutes, TIFR has a lot of observations, Inter-University Center for Astronomy and Astrophysics, Institute of Astrophysics, and Plasma Research Laboratories. These are the major. And Aryabhatta Research Institute in Uttarakhand. These are the major astronomy research institutes. And you can see this quickly. And in Institute of Astrophysics is you can see the right bottom side is our main center, and which has 50 scientists, and then we have 90 PhD students and things like that. And then this is the one of the oldest large observing facility in the country. So we run actually 2.3 meter telescope. It's a very beautiful place. Till recently, this was the largest telescope in the country. And then very recently, it was the largest telescope in Asia. Okay. So we do go there and observe. And then this is the new, this is the facility. This is the telescope. You can see this one here. And then this is the SL spectrograph, which I said we can have a very high resolution spectra using this, and then get data from these stars. And then we also ran very large facility in Western Himalayas, which is located in Hanle in the Ladakh region. That is now currently we have 2 meter telescope, and then now India is planning to have a large national solar telescope close to that, and then we also are planning to have a 10 meter class national large optical and infrared telescope there. And it is a very dry place, and then you don't have any monsoon issues, and most of the time skies are clear. That's what we look for. And this is the telescope, the Himalayan Chandra telescope. And then there also we have a very nice, very efficient spectrograph there. And then we have these, sorry, there's a picture got mixed up. This is something else. So then we have the 3.6 meter. This is the newly commissioned largest telescope, optical telescope in the country, which is now located in Devasthal. You can see that Devasthal, Aries, Nainital, which also have many other places. So this is also one of the very good site for astronomy. And of course, you have the radio telescope, that is GMRT, that is Giant Meter Wave Radio Telescope, which is the largest in the world in that particular wavelength. And of course, we have recently launched the Astronomical Satellite, which is now in the space, which is producing a lot of data. And then a lot of people, but mostly in ultraviolet and X-ray mapping of the sky, and which is still producing a lot of data for astronomy. And then IAA made the main payload for this called UV, ultraviolet telescope. But these are very small because the space thing is very demanding. You cannot take it very big telescopes up, particularly in India. And this is the UV satellite which IAA produced. And you can see the down figure, left side. And this is the NASA's ultraviolet image. And then this is our AstroSat image, which is much more higher resolution compared to NASA's GALAX telescope. So this is doing a fantastic job. And of course, now India is now planning another space mission, which is Aditya-1, which is now scheduled to be launched in 2021 in the beginning, which is a major astronomical facility for the sun, which is going to be in the L1, that's the Lagrangian point 1, which is basically 101.5, 15 lakh kilometers away from Earth. Okay, so this is going to be synchronized with sun's movement, so that you can see the sun all the time, day and night, no obstructions by the Earth. So that you can see that is a satellite facing the sun all the time, and then you go with along with the Earth orbit. And then, of course, now we are planning another 2-meter class telescope. That is solar telescope. That is going to be in Ladakh area, Pangong Lake, and they have now smaller infrastructure. You can see that infrastructure, and then see the model of that, which is inserted here. That's a telescope. Of course, this is a site which we are looking for national large optical telescope as well, the Ladakh area. That is because very dry place. Normally, people look at most of these are very exotic places astronomy has, because that is because you wanted to be away from people, light pollution, and you need to have very clear nights for throughout the year. That means less rainfall, and also you don't want to be humid places, because the humid places, what happens is a lot of water vapor is there, which absorbs a lot of, lot of water vapor. So that's not good for it. And then also you do want to have a stable atmosphere, less turbulence in the sky, So because of the turbulence, you see, twinkling of stars. Twinkling may be romantic and then good for movies, but for people, but then it's not good for astronomy. You wanted to have very stable images. So you have very stable atmosphere. That's why you go higher in altitude. So you have the less atmosphere. So that's another reason you want to have very isolated places on Earth. Okay, so now let us switch gears to India's participation in the 30-meter class telescope, a new window to the universe. Okay, this is the project which now India is part of it and trying to build a number of things. To give a perspective of the size of the diameter of the telescope, you can see now the India's largest 30-meter telescope, 3.6 meter, which you have recently commissioned, is a 3.6. That is Devasthal Optical Telescope. That's what we have. And then our own Indian Institute of Astrophysics, Venubapu telescope is 2.3 meter. And then the currently largest telescope on Earth are Keck 10-meter class telescopes. And now we are going to have this TMT 30-meter telescope, which has its own challenges. Challenges are not just making it, but challenges are getting the surface images possible and reaching the universe almost when the universe was around 500,000 years old. That means you have to reach stars almost when the universe is very infant in stage. That's what we're looking at. Hello, can you hear me? Hello.
Yes, sir. Yes, sir. You're audible.
So what happened? These slides are not moving. Hello, Shirish.
Can you close the presentation and open it again, sir?
Funny. Even I'm unable to close. Something happened. Okay, fine. Got back. Oh, it's taken too long. Okay, something wrong. Oh, maybe these are. What? Huh? What happened? Huh? Stop sharing. Okay. Can you hear me, Nitish?
Yes, sir. You're audible.
Okay, good. So let me share again quickly. See. Can you see my screen? No.
Yes, sir.
Oh, good. What is happening? Okay. Are you able to see screen?
Yes, sir.
Okay, good. Okay. So let us see. So there's a bit, these are the basics about, thank you. Why do you want to have larger and larger telescopes? You can see this flux is basically proportional to the diameter of the telescope. You can see the d square, that's what it is. And also you require larger size of the telescope, then the resolving power is also goes higher, better and better. So the d is the denominator here. The denominator increases, means you can see the theta becomes smaller. That means you can see things much finer details. That's what it happens. So the TMT is going to be fitted with state-of-the-art adaptive optics system. I'm not going to say anything about what happens is now adaptive optics is basically you have these more than 100 kilometers of atmosphere between your telescope and then your stars. So what atmosphere does is basically creates turbulence. Because of the turbulence, it has a different refractive indices. That's why you see the twinkling process. When the stars move, because when the atoms move, the layers move, and the turbulence, the refractive index keep on changing from one layer to another layer, and then you see a twinkling star. But now what to do is, the adaptive optics, the technology is, you had to make sure that these turbulence are completely minimized by modeling it, by getting the data of the turbulence information onto the telescope and then making as if the telescope is in the space. So that's what this adaptive optics is going to do. This is a huge technology, which is now there in many telescopes, but then attaching this to the TMT is going to be a huge benefit. Okay. That's what you can see, what the atmosphere is going to do clouds. You can see distorted wavefronts. So now you have to take these distorted wavefronts onto the telescope and then detect those wavefront distortions and then correct them to planar waves. That's what the adaptive optics is going to be done. So this is a twinkling of the stars. You don't want to see them. Okay, that's because of the distortions. What you want to see, I'm not going to discuss this. Maybe once I come to IIIT Kurnool sometime later, probably we can discuss more on these things. Okay. That's what you see. You can see this is uncorrected image, one of the largest telescopes on Earth, that is uncorrected one. But then you can see, if you use adaptive optics system, you can see diffraction limited images as true. You can see that. See, you can see the clarity from left to the right because of the adaptive optics. I think this is a buffering it. Okay. So there are a lot of issues people wanted to understand using these large telescopes. And then one of them is, you might have read somewhere, the expansion of the universe. There is it got a Nobel Prize recently. This is one of the issues because you want to see much more farther into the universe to measure distances and then see whether the universe is still accelerating forever. Okay. And where the telescope is going to come up, it is going to be in Hawaii, a place called Mauna Kea, which is already home to many large telescopes, which you can see in the background. Okay, and our telescope is going to be here. And this is one of the best sites on Earth for large telescopes. Okay, you can see that the Mauna Kea, and these are the partners. So India is one partner, China is a partner, and then you can see Canada partner, and US, and that's what this is. This is somewhere in the middle of Pacific Ocean, Mauna Kea, and which one of the best sites, and then which has less turbulence for astronomy to do. And that's the site. So the seeing is basically the level of turbulence in the sky. So what India is going to do is India is going to produce, supply a lot of items which are required for the telescope. So this is one of the segment. I didn't tell you this 30-meter, you cannot make a one single 30-meter telescope, 30-meter diameter glass. It is very difficult to manufacture a single piece of 30-meter diameter. So what we had to do, we had to make it as segments. So now it contains this TMT 492 segments. Each segment is around 1.45 meters, and these are placed together. The technology involved in this is all 492 segments have to behave like a single mirror all the time during your observations, as the entire system is tracking the sky at few nanometer levels. That is the criticality of the telescope. So for which you need to have very high precision optomechanical systems, which now we are working on. So India has to produce various aspects of it to make these 492 segments act like a one single mirror, which requires a lot of sensors. This is one of them. I put one mirror system. So such mirrors, we need to have 492, I have to put together, and each mirror is separated by 2 millimeters. Okay. So these are the both optics, sensors which are required, and a lot of software is also required. So India is making a lot of hardware. You can see large number of more than 20 companies are involved in producing sensors and then actuators, and a lot of testing goes on here. And then we also made now, in India, we don't have any large facility for large optics facility in the country, both in the private or in the government. The ISRO produces now around 1.2 meter mirrors they fabricate, but that takes very long time, anywhere between 18 months to 24 months, one single mirror. The technology now we are looking at it, every single mirror has to be manufactured within 2 weeks. That is a new technology which we are developing. So because we wanted to make 492 segments, it takes a while. So that's why all the partner countries are taking up this job, okay? Because each country, every country among the partnership wanted to make these, use this technology and then develop their own technologies. So recently we built state-of-the-art lab in Bangalore, around 40 kilometers from IIA, which is called Osakote. And then we got these blanks inspecting, which come from Japan. Those are free issued by Japan as a contribution to the TMT project. So now we had to polish them, which is a completely new technology, which we are going to be installing here. And these are some of the pictures, how we came to the TMT into the picture. You can see it is a long affair. So it is almost now 10 years we are into the picture. And then 2013, we signed as a, scientific authorities, certain documents, all the partner countries. This is in Hawaii. So the Hawaii, you can see the traditional garlanding everybody has to wear. So I didn't have the Hawaiian t-shirt there that time. So, and then we had in 2014 groundbreaking called Bhumi Puja, and then I was there representing India, and then along with me, Honorable Ambassador Taranjit Singh Sandhu. Now he's a Indian ambassador to United States of America. So that time Jaishankar was there, and then he sent Deputy Chief of Mission for this groundbreaking in Hawaii and Mauna Kea. And then what happened was during the groundbreaking, it was quite unexpected. And then a lot of native Hawaiians came up the mountains, and then unfortunately, the program got disrupted in 2014. And then it went to Supreme Court and things like that. And then project has now all the legal aspects now. Legally now we are free to go, but then still we have a problem with native Hawaiians. We are working with them. We are telling them science and cultures and religions can work together, coexist. Astronomy being a completely non-polluting. So we are trying to negotiating with them, but it took a while. And then as a plan B, then we have another site, which is in Canary Islands in Atlantic Ocean. And then we are now assessing the situation with the protesters still, which are going on. A lot of American government is negotiating with them. So hopefully we'll start constructing soon the project. And this was the Indian government approved. So at that time, you can see Honorable Minister for Science and Technology, and then handing over signed papers. And then you can see Vijay Raghavan, and then who is now currently advisor to the Prime Minister. And then I was receiving these papers. And then that is the 30-meter telescope of 5 partners. You can see different languages. Thank you very much. And then I'm happy to ask any questions if you have. Hi, Suresh.
Thank you, sir.
Sorry, I took more time than assigned to me.
Oh, no, that's not a problem, sir. Sir, we have a question from the chat. Most of the lithium we now see is from supernova explosions. So, sorry, is most of the lithium we see now from supernova explosions, or is it from the Big Bang?
Yeah, the large, yeah, quite amount comes, significant amount of comes from the Big Bang. But of course, now it increased by 75%, 4 times. And that comes from supernovae. Supernova is one of the things because it produces very high energetic particles, which can smash higher atoms like carbon and oxygen. They can produce lithium as well. But then when you look at all of these things, which is not sufficient to account for these 4 times increase. So people were looking for new sources. So then now the stars seems to be the significant source of lithium in the universe.
So can you tell us a little bit more about the telescope in Himachal Pradesh?
That is in Uttarakhand.
Sorry, Uttarakhand.
There is a 3.6 meter telescope in Uttarakhand, and that is recently commissioned. Of course, that is in both in optical and infrared telescope. So, yeah, I don't know what you want to learn more about that, and then people who can really look at the ARIES website, which is Aryabhatta Research Institute controls it officially. And of course, now we have new sites in the Himalayas, Western Himalayas, that is in Ladakh area. It's close to Chinese border. So, of course, we have a small modest telescope, they're 2 meter, but that is, we run from Bangalore. We have the satellite link from Bangalore. We run from here entire thing. So
with SpaceX becoming bigger and bigger,
yeah,
we have more and more small satellites flying in space.
Yeah.
They cause a lot of distraction, I guess you could say. So how do you see that impacting ground-based observations?
Ground-based observations are not going to be affected, but of course, you mean to say space telescopes are becoming normal? That is how that
Yes,
is
sir.
going to affect this thing.
No,
Yeah,
no, sir. I meant,
space is very important, and then you don't have this atmospheric problem, but that's going to be very expensive to launch telescopes. For example, Hubble Space Telescope. In today's cost, though it is a 2.4 meter telescope, I think 2.5, 2.4. So it's quite expensive. So it ran into some few $1 billion. But currently there is a new telescope which is NASA is launching. That is 6.5 meter telescope, James Webb Telescope, which is almost now $10 billion the bill. So, but then with these technologies like adaptive optics, and then people are going to beat that advantage very soon.
I think Murli sir had something to say.
Yeah, sorry. Like I have also some. Thank you, sir, for this enlightening lecture. It was really.
Thank you very much.
It's a grand talk. Your first part as well as the second part TMT. So I have like a couple of questions related to the first part.
Sure.
It's not still clear to me. You have this nucleosynthesis theory.
Yes.
You have the new data. Is there like that? For example, you were telling that the flashing of the lithium is a transient phenomena. This theory has to be modified, or like it is consistent with the like.
The problem is not the theory. Theory is correct. In the way you see, you have the laboratory, the cross sections of the various reactions. These are all known very well in the lab and things like that. They can do. You produce lithium, but the main mechanism is how to bring that very fragile, very reactive element like lithium to the surface without getting destroyed. So that is a very key. So now what we need to understand, there is not much study about this helium flash issue. Okay, you make these observations, you can see that brightness versus the temperature diagram. You can see where the stars evolving in the diagram, but then there are many issues which we don't really understand. One of them is that helium flash issue. What exactly is going at the center, and then what are its effects on the overall the effects on the surface of the star, like the elements and things like that. Why lithium escapes from the center to here without getting destroyed, without getting proton capture. That is an issue which we don't know yet. So that's another aspect which now people have to get into real theoretical and hydrodynamical simulations, what happens at the core. And then looks like this lithium is also, it's a short-lived. So it's not there for long. So not more than 100 million years. That's what we are looking at it. So.
Okay, sir. Thank you, sir. And my other question is related to TMT, because you mentioned that there's a lot of technology there. How that the present generation, like students can, if they're interested, can get involved in this project, like internship or like.
When we started these big projects like India's participation in these large telescopes like TMT, which requires a lot of human resources. So in the Indian Institute of Astrophysics, that time we have only a PhD program with science backgrounds. And then looking at these projects, which are mostly in engineering in nature, we started this called MTech PhD program. Okay, that is, we wanted to create astro technocrats, astro engineering. Yeah, so that program is extremely successful at IIA. It's running on now last 8 years, and we do get 8 or 9 people every year. And then these people are registered with Kolkata University for MTech program. And if people don't continue their PhD, after 2 years, they can take MTech degree and then go away. And if they want to continue, they can continue in PhD. They get PhD in astronomy. So far, nobody left, and then everybody continued in PhD. But all of them are doing pretty well in various places. Great demand. They are in Europe. They are in Caltech. They are in University of California doing great stuff with astronomy instrumentations. Astronomy instrumentation is one of the top-notch things because the demands are quite high from the science community, and then meeting those demands are extremely difficult. Of course, it's rewarding. So, yeah, people can. Of course, India TMT also offers quite a number of internships and things like that, both in software, mechanical. We also have training engineers and things like that. People come and then do some 6 months and then go. We had quite a number of people like coming and then going. So.
Nice, very nice. I think
Yeah.
most engineers who are watching, I think they can.
Oh yeah, a lot of people got very good exposures because it's not only even training engineers are quite exposed to all these 5 country partners, almost on daily basis because there are a lot of meetings. Looking at reviews, looking at all these kids, engineers are participating in those talks and then learning, and it's a very good exposure to everyone. Technologies from labs from Japan, labs from Canada, and whoever has done within India TMT all got terrific jobs abroad and then they went. So, and we hope they come back later on and contribute to our own astronomy programs in India. So, yeah.
Yes, sir. Thank you, sir.
Yeah. So these webinars are quite good, actually. The less stress on hosts and less stress on speakers. But only the drawback is we can't see people, audience, whether they are sleeping or, reading some books or looking at WhatsApp or Facebook. So, but otherwise it's a great medium. And hopefully you guys add more experience to these, the media, adding 3D, effects and things like that. So, yeah.
Sir, I had a question.
Please, Sarish.
So how much of astronomy is actually observing things and how much of it is just processing data?
See, in astronomy, there are 3 branches. One is theoretical, the observational, and then the other experimental. The experimental people, they look at it, astronomical instrumentation. What kind of instruments are required to achieve certain science goals? And the theoretical people, they both handle the processed data, which is published, and of course, theoretical modeling, simulations, use all sorts of data, manipulations and things like that. And then, of course, putting theory forward. We have seen, Chandrasekhar Subramanian is a theory about white dwarfs and then degeneracy. And then that was proved by observations only after the many years, maybe after 40, 50 years later on. And then for which he got a Nobel Prize in 1982 or something. So that's a theory part. It's a pure physics. Astronomy is also basically physics, but then objects are somewhere else, the physical process. And then observations requires both data analysis and observations. It's not just observations, you have to do all kind of things. It's a quite involved job, astronomers, in the sense, when you go to observations, you get 10 nights, and then sometimes all the 10 nights gets washed away by unpredictable weather, because particularly I spent so many nights in Kavaluru observing, go there for a month, I get 1 night of observations. But what happens is that complete program gets delayed if you can't get during that time. Then now those stars, which becomes very closer to the sun, they become the daytime, after 6 months period. So then you have to wait another 6 months to get those stars if you miss. So that is another drawback for observational astronomers. So if you miss that time, you wait for long. So so throughout night, I had to wait for those better skies. So that's one reason it takes a while to get PhDs in observation sciences. And then you have to get all the data, and then you have to clean up the data, and then if something gone wrong, it's not something like tomorrow you can rectify it. You wait for another next year. You put a proposal and things like that, and then get time. So. So,
Sirish?
Yes, sir. I think
some
we're
questions are
done with
there?
questions. Sir. No, sir. I think we're done, sir.
Okay.
Thank
Suhas want to.
you.
Yeah.
Oh, go ahead, Devraj, please. Murali, go ahead.
Yes, sir. Like, thank you, sir, for this kindly accepting like this our invitation, and then like you are very busy person. Like you are a program director for it's a huge project, and then it is also proud for every Indian that you are part of this project. And then we are looking forward to in the future also to collaborate with you. And then you can, whenever you visit Kurnool, you can visit
Sure.
to
I will make sure this time I visit, and
Yes,
then probably we can give talk on some of these issues much more in detail. So
yes, sir. Yes, sir.
yeah. Thank you very much for providing this opportunity. It's very nice of you all. So
Sirish,
Yes, sir.
Suhas is ending.
Yes, sir. Sir, we are here, sir. We do not have any other questions from YouTube also, sir.
Okay, sir. Then
Thank you.
Thank you, sir. Thank you very much.
Thank you very much. Yeah, we'll talk later on. Huh? Yeah,
Yes, sir.
thank you.
Thank you.
Bye. Bye.